Hello humans, my name is Professor Leach, and today we're going to continue our journey of trigonometric substitution. Trigonometric substitution is for integrating quadratics that can be factorable or not, that usually show up under square roots. The idea here is that when we have the square root of two terms, this is trouble, but this is trouble that trigonometric substitution can solve. In particular, we should note that we have the square root of two terms, and I don't have the option of just substituting this stuff under the square root because I don't have the derivative of that as a factor. So that's why we have to resort to trigonometric substitution. So let's review the roadmap of trigonometric substitution. That's where we have an integral f of x to x. And this integral has something like this. A quadratic, factorable or not, probably under a square root, and we can't do some other substitution on it. So we talked about the three different acts of trigonometric substitution. Act 1 is to do the trig sub. That's the second thing that we learned about this. This is how we go from our integral in x to our integral in theta. At this point, we should be looking at a product of powers of trig functions, and we should expect to see even powers of cosine or odd powers of sine. So once again, f of x has quadratics, probably under square roots. So f of x has quadratics, and they're probably under square roots. We do the trigonometric substitution, and now we should be looking at a product of powers of trig functions. Product of powers of trig functions. We should be looking at a product of powers of trig functions, probably an even power of cosine or an odd power of secant. Then we do Act 2, which is the integration part. So then we're going to integrate into, an antiderivative in theta. This is Act 2. This is where the integration happens. We did not want to integrate in x, so we integrate in theta instead. And then the last thing that we need to do, which is the one that we haven't learned yet, is to go back to our original variable, which is what? The function that we're looking for. So Act 3 we do the untrig substitution. And it's a little bit more involved than just replacing w's with x squareds or whatever they were. But this is where we have the antiderivative in terms of theta. And then our final answer is an antiderivative in terms of x. Nice, simple 3-act structure. We have quadratics under square roots. We do the trigonometric substitution to rewrite the integral this trigonometric substitution part is not part of the integration process. It's just rewriting the integral into a product of powers of trig functions. Specifically, it's taking care of this square root of 2 terms problem. That's trouble, and this is how trigonometric substitution solves it. Now we're looking at the product of powers of trig functions, probably an even power of cosine or an odd power of secant. So then we integrate to find an antiderivative in terms of theta. And then we have the next big thing that we need to learn is how to untrigonometric substitution. All right. So let's take a look at another example of Act 1, or let's remind ourselves of the 3 cases of Act 1. Let's remind ourselves of the 3 cases of Act 1. So this tells us what we're replacing x with, what we're replacing the dx with, and the Pythagorean identity that's going to take those 2 terms into 1 term. Those are the things involved. What's x equals? We need a dx, and we need a Pythagorean identity that turns 2 terms into 1 term. So we need x equals. We need to write down what dx equals. And then a Pythagorean identity to turn 2 terms into 1 term. All right. So the 3 cases are the sine case. The 3 cases, I think columns, are the sine case, tangent case, and secant case. I'm going to lead with tangent case today because that's my first example for today. Oh, I also got to list what we are looking for to trigger each of these 3 cases. In the tangent case, we are looking for something of the form a squared plus x squared. This is equal to x squared plus a squared. It's just normally written this direction. So if we see something that says a squared plus x squared, if this is the quadratic that we have, then we're going to do the tangent case and we're going to substitute w equals a tangent theta. If, sorry, we're not doing w, we're doing x. We're replacing x with a times tangent of theta. If x is a tangent of theta, then we take the derivative dx. The derivative of tangent is secant squared. And that's how we translate the dx into a d theta. And then we're going to need the fact that 1 plus tangent squared is equal to secant squared. So those are the things that we need in the tangent case. Next up, we have the sine case. Which has the form a squared minus x squared. In the sine case, we make the substitution x equals a sine theta. The reason that we want the sine is because we want 1 minus sine squared to become cosine squared. The reason that we want the a in front of it is so that we can factor out the a. So we get a squared times the quantity, a squared times the difference, 1 minus sine squared. So x equals a sine theta. That means that dx equals a cosine theta, d theta. And the Pythagorean identity that we'll need here is that 1 minus sine squared theta is cosine squared theta. The substitution we're making, the dx and the Pythagorean identity. And finally, we have the secant case. This is where the x is positive and the a is negative. So x squared minus a squared. This is the case where we use x equals a secant theta. We're going to, if x is a secant theta, then dx is a times secant theta, tangent theta, d theta. And the substitution, the Pythagorean identity that we need is going to be secant squared minus 1 equals tangent squared. So identifying the case tells you what the case is going to be, because if you just remember the three Pythagorean identities that we're going to use, 1 minus sine squared is cosine squared. So that tells you that you're going to use sine with a squared minus x squared, because the x squared is where the sine squared shows up, and we'll have 1 minus sine squared. 1 minus sine squared is cosine squared. For the tangent case, it's the plus, because 1 plus tangent squared is secant squared. For the secant case, it's positive x negative a, because secant squared minus 1 is tangent squared. So these are the substitutions that we make, these are the substitutions that we make depending on the quadratic that we're looking for. Remember what trigonometric substitution works for. It works for quadratics, factorable or not, usually under square roots, which is what's causing the problem. All right. Let's look at another example. I have to switch pages. I can try to fit it. No, I can't. Let's switch pages. All right, so let's look at another example. Yesterday, they were both square root of whatever the case was. So I want to do something a little different. Yeah, there we go. So today, let's look at an example. And we're just trying to do Act 1. We're just trying to get from the integral that we're about to write down to the products of powers trig functions. Let's suppose that we have the integral of 1 over the square roots of, instead of just 9 minus x squared, I'm going to do 9 minus 25x squared. Oh, wait, I don't want minus, I want plus, because I wanted to do tangent case. I even said that at the top of the hour. So we see that there is the tangent case, because it's a squared plus x squared. And we also see there's a coefficient 25 in front of the x squared. Also, we have the square root in the denominator, which doesn't change how we make our decision. So we've identified this as tangent case, but we also notice that there's a coefficient in front of the x squared. And you're thinking, Leach, you said that it was going to be a squared plus x squared, not a squared plus b squared times x squared. What gives? So rather than worry about these separate cases, we're just going to make this look like what we want. So we notice there's a coefficient of the x squared, and we want a coefficient of 1. So we want the coefficient of x squared to be 1, but it's 25. So we make it 1. We just hit it with the algebra stick. You want the coefficient of x squared to be positive. It's being multiplied by 25. just factor out the 25. What it's going to look like is I have 9 plus 25x squared. I'm going to factor out the 25, and that'll leave 9 25ths plus x squared. If we factor out a 25, now the coefficient of x squared is 1. And in this case, a will just be 3/5. So we factor out the 25. Now the coefficient of x squared is 1. Factor out the 25. We factor out the 25 to get the coefficient of x squared to be a 1, which is what we want. Because what we need it to look like is a squared plus x squared, not a squared plus something times x squared. So that was a little bit of algebraic chicanery that I wanted to introduce to you. So I'm going to replace my square root of 9 plus 25x squared. That's going to be the square roots of 25 times 9 25ths plus x squared. And this is still all under 1. And we're still integrating dx. We're just doing a little bit of algebraic setup here. So by factoring out the 25, and you can see the reason why I picked a square, 1 over the square root of 25 is just 1/5. And so now we have an easy tangent case. So 9 25ths plus x squared, I'm going to do the tangent case, and x will be 3/5 tangent theta. So now we're going to factor out. We're going to factor out the 1/5 because we can take 1 over the square root of 25 is 1/5. So that's where that came from. And I'm going to pull it completely out of the integral as I normally do. In the denominator, I have a square root of 9 25ths plus x squared to x. So now we have a coefficient of 1 for x squared. We're ready to apply the tangent case. What's being squared to get 9 25ths is 3/5, so x will be 3/5 tangent theta. Dx is going to be 3/5 secant squared theta, d theta. It's going to go in for the dx. And I'm going to remember that 1 plus tangent squared is secant squared. So, keeping track of everything. Really, this is all just about keeping track of all your stuff. One part of it is knowing what steps to perform. The other part is, of course, just keeping track of all your stuff. So I'm going to have a 3/5 tangent squared. I didn't say that right. I'll have the square of 3/5 of tangent theta. Oops. Also, for some reason, I switched the order. Sorry. And I'm going to replace the dx with 3/5 secant squared theta to theta. No, I have space for it. So now that I've made the substitution, the thing happens. The reason that we're doing this happens. 3/5 tangent squared is 9/25 tangent squared theta plus 9/25. We can pull out a 9/25 and we're left with a tangent squared theta plus 1. That was the goal, to get at that tangent squared theta plus 1. It's why we had to figure out this coefficient, and it's why we use tangent. And tangent squared plus 1 is just secant squared. So I've got this 1/5, and I'm going to multiply it by the 3/5 to get 3/25 out in front. So this is from 1/5 times the 3/5 from the d theta. Remember, this is just bookkeeping. And now I have 1 over the square. I'm going to put the secant squared on top. That's convenient for me. And then in the denominator, I have the square root of 9/25 secant squared. So my denominator is the square root of 9/25 secant squared theta. In the numerator, I have the secant squared theta d theta. Pause for copying. Then the thing that always happens, the other benefit of this process, we also get rid of the square root. The square root of 9/25 secant squared is 3/5 secant. So now I can simplify some stuff. So I've got 3/25 times the integral of square root of secant squared is just secant theta. And on top we have secant squared theta. And this is still d theta. Oops, secant theta is times 3/5. I got 3/25 divided by 3/5. So now I remember, I was thinking, I don't really need to multiply by this 3/5 out in front. And now I remembered why. Actually, I remembered it as soon as I did it, but 3/25 divided by 3/5 is going to be 1/5. And then we're going to have this secant squared divided by secant is just secant. So we end up with 1/5 back to 1/5. The integral of just secant theta d theta, which is one that we know how to do. So this 1/5 coefficient is 3/25 divided by 3/5, which is 3/25 times 5/3. So it's this 3/25 on the top, and then it's 3/5 with the secant on the bottom. Divide those out. Secant of theta is one of the integrals that we know. So this is the end of Act 1. So at this point, Act 1 is complete. We have transformed our original integral in x with its quadratic under a square root, and we have translated that into a 1/5 secant, an integral of the product of powers of trig functions. Act 2 would be to integrate the secant. So we have 1/5 the integral of secant theta d theta is 1/5 the natural log of the absolute value of secant theta plus tangent theta plus c Now we've integrated. We're at that g of theta state. We got the antiderivative in theta. The next stage would be to perform act 3. And that will get us back to our original variable. Any questions? Here's one of the things that you're not going to like about trigonometric substitution. The whole first act has no calculus in it. I suppose that we have to take the derivative of tangent is secant squared, but it has very little calculus in it. We're not actually integrating anything. All the way up to this point where we wrote integral of secant theta, this is just setting up the integral that we're going to do. This is all the work that we have to do to set up the integral that we're going to do. This is until we recognize 1 over the square root of 9 plus 25x squared. And we say, this is 1 over the square root of a squared plus b squared x squared. So that's just going to be a 1 over b secant. So until we start recognizing the integrals that we start with. Most advice for this particular problem, starting off with 1 over 9 plus 25x squared, is someone will say, just look that up in a table, which is very archaic. I don't know if anybody under the age of 50 would tell you to look something up in a table. Because if someone says, look something up in a table, you should say, oh, you mean Wolfram Alpha? It's like, oh yeah, I'm trying to actually learn something here. Looking stuff up on Wolfram Alpha when you're trying to learn how to do trigonometric substitution is like watching videos of people work out. It doesn't work. That's not how this works. We're trying to make ourselves stronger. So we're going to do the work. But this is all very routine. We blast it with a lot of calculus. Sorry, blast it with a lot of algebra. Beat it with the algebra stick for a little while. We've done the integration part. The next thing we need to do is figure out how to go from theta back to x. Any questions up to this point? All right. So let's look at Act 3, where things come full triangle. This is the untrigonometric substitution part, going from theta back to x. So I'm going to use the example that we just did because it's convenient for us. So remember, we started off with the integral of 1 over the square root of 9 plus 25x squared dx. We did Act 1 and Act 2. Let me write down the substitution we made. We made the substitution x equals 3/5 tangent theta plus some other stuff. We did Act 1 and Act 2. And we ended up with the natural log, 1/5, the natural log of the absolute value of secant theta plus tangent theta plus c. So after Act 1 and Act 2, this is our antiderivative in theta. We need to get our antiderivative in theta into an antiderivative in x. So here's what we need to do. So notice that one of the theta terms in our antiderivative in theta is just the tangent. And I can solve for the tangent pretty easily. If x is 3/5 tangent theta, that's my original substitution. I can solve for tangent of theta and get tangent of theta is 5/3 x. So that's where we start. So if x is 3/5 tangent theta, then tangent theta is 5/3 x. That takes care of that, but what about the secant? So what we're going to do is I'm going to, so this takes care of the tangent, but what about the secant? Yikes. So we still have that secant to fix. Here's what we're going to do. I'm going to look at 5/3 x. I'm actually going to write it in a more convenient form for me. 5x over 3. So I'm going to say tangent theta is 5x over 3. And I'm going to remember that tangent is opposite over adjacent, and I'm going to draw a right triangle. So I'm going to draw a triangle with a theta in it. So tangent is opposite over adjacent. If I put theta down here, then opposite is 5x and adjacent is 3. And then I'm going to solve for the hypotenuse because I need an expression for secant theta. So secant theta, if I look at this right triangle here, the hypotenuse is going to be the square roots of a squared plus b squared, which is going to look very familiar. So in this case, the hypotenuse is going to be the square roots of 9 plus 25x squared. So we identify the opposite adjacent and fill in the hypotenuse. If you're looking at this and saying, isn't this what started this whole process? Yeah, this is what started the whole process. Now what we're going to do is we're going to remember that the secant of theta, secant is 1 over cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So secant theta is hypotenuse over adjacent. Hypotenuse is square root of 9 plus 25x squared, and adjacent is 3. Now I've got an expression in x for the secant of theta. So our final answer is going to be 1/5 the natural log of the absolute value of the square root of 9 plus 25x squared plus the tangent of theta, which is 5/3 x. Plus c. Oh, I meant to write this in purple. Oh, well. And this is our antiderivative back in x. So that's how we take care of Act 3, going from theta, our antiderivative in theta, to an antiderivative in x to get our final answer. We would probably write this in some different form. So let's go over to the Wolfram Alpha. No, I'm not going to bother sharing screens. And let's just look at the function. What did I put? 9 plus 25x squared to the negative 0.5. Let Wolfram Alpha think about it for a while. Let's see, and see if it will give us a nice indefinite integral. So if you take a look, so give you a minute to take a look at what we've written, because we found this antiderivative with trigonometric substitution. And then we can look at what it looks like when we find the antiderivative with Wolfram Alpha. This is one of the super glaring examples where you just plug things into Wolfram Alpha, say, man, that looks so simple. And then you just copy that down. In which point I say, no, I said to do trigonometric substitution. And then you're like, oh, but I did do trigonometric substitution. Then I'm like, oh, show me. And then like, oh no, I'd have to pay for Wolfram Alpha to have the step-by-step solution shown.
Professor, did you?
Go ahead.
Oh, I was just going to ask, did you input the whole equation, or just all I'm seeing is the 9 plus 25x raised to the second power square root?
So if you scroll down, one of the entries in Wolfram Alpha should be the indefinite integral.
Got it.
Because I just put this into Wikipedia for math. And so Wolfram Alpha is telling you that it is 1/5, that's the 0.2, by the way. So 1/5, the inverse hyperbolic sine of 1.6 repeating 5/3 x plus c. Because Wolfram Alpha is like, oh, dude, this is why we have hyperbolic trig functions. And you're like, but what is it in the, what does it look like if we didn't just look it up? Let's see what the step-by-step gives us. No, that wasn't the step-by-step. This is the step-by-step I wanted. Yeah, it tells you to do trigonometric substitution, but it doesn't tell you how it goes from this natural log business to the hyperbolic sine. The inverse, the inverse hyperbolic sine. So it also writes decimals. So that's the other big clue that you just used a machine, because your 1/5 will show up as 0.2, and you'll have all these 1/3 running around. At which point I'll probably just give you the points anyway, because I mean, if you're not going to do the work because you don't want to learn things, I mean, why should I even bother forcing the issue? If you're not willing to do the effort to learn trigonometric substitution because you deem it unimportant, and you're just going to look stuff up on wolframalpha.com, why am I going to fight you? Why do I feel like I have to get revenge? I don't know. Some teachers are too adversarial. I mean, if that's what you're going to do, that's like hiring a personal trainer and then just not putting any effort when you're there. Like, why did you do this? What was the point? And I know exactly what the point is. The point is that you don't really want to learn how to do calculus. The point is that you want certification from me that you can go on to click the next box, Calc 3 or whatever it happens to be. So I guess that's just a game that we're going to have to play. Any questions? Comments? Snide remarks?
I was wondering if you're going to let us have that one.
All right. So we have now done trigonometric substitution, a play in 3 acts. We've had to learn all 3 different acts. Act 3 depends, how Act 3 plays out depends on what we made the substitutions. So if we had made the substitution, for example, if we had made the substitution, we did this one yesterday, x is equal to 3 sine theta. Then we can solve for sine theta. We might have sine theta, we might have cosine theta, we might even have just theta. So we can write this, if we need sine theta, sorry, stumbling over my words. I don't know if it's a more coffee thing or a less coffee thing, but I know what I'm going to apply. We can solve for sine theta and write that as x over 3. If we need theta, we can just do a sine inverse of x over 3. If we need cosine, which is something that could show up with sine, we're going to be integrating even powers of cosine, so some cosines might show up. That's when we read x over 3 as opposite over hypotenuse. Draw ourselves a right triangle with theta. X is the opposite, 3 is a hypotenuse, and then solve for the adjacent side, which is going to be the radical that told us to do this trigonometric substitution in the first place, 9 minus x squared. Then we write cosine of theta as adjacent over hypotenuse. Adjacent is the square root of 9 minus x squared, and the hypotenuse is 3. Now we have expressions for sine of theta, theta, and cosine of theta, whatever might show up. Any questions? One thing, last thing for today, the one thing that you will absolutely not do is solve for theta. Actually, this is, I don't know if this is a general thing. I don't know how many professors think that this is lazy as I do, but not once you have theta, you do not write cosine of theta as cosine of sine inverse of x over 3. That's trash. Don't be lazy. Don't write it that way. So absolutely, once you get theta, do not, at least in my presence, do not write cosine of sine inverse of x over 3. So you absolutely, once you have the theta, you don't just get to plug it into this trash. You've got to write, you've got to go into, you don't have to draw the triangle. You can know what's going to happen. So you don't have to draw the picture. I don't care about the picture. I care about this expression for cosine of theta, square root of 9 minus x squared over 3. I don't know why this notation makes me so angry, but it does. This is one of the pet peeves that you're going to have to deal with me as your professor. Later on, maybe your next professor is totally cool with you writing trash like cosine of sine inverse of x over 3. I don't know what but they'll have some other hang up that I find innocuous. But that's going to be their thing. This is mine. And one of your jobs as a student is to figure out the idiosyncrasies of your professor so that you just don't do those things. At least in your case, your professor recognizes this is some weird ass idiosyncrasy and it makes me really angry. So I'm just saying, just don't do that. The reason that I put that out there is once I've said this is a thing that I'm saying that you shouldn't do because it makes me annoyed. If you do this, now I know you're coming after me personally. Now I know you're just trolling me. And penalties are much harsher when you're trolling me. If you just get things wrong,
That's the whole point of this exercise. But if you start deliberately getting things wrong, then it's on,
Otherwise, they're doing it irregardless.
irregardless. Apart from that, I believe that's it. I'm done. Email this to your grandma, and I'll see you some other time.